What if the universe is not as random as it seems? What if every star, every galaxy, and every cosmic event is part of a grand, hidden design, a pattern so intricate that it has eluded us for centuries? Picture this, a single thread of light stretching across the cosmos, connecting galaxies in a web so vast it defies imagination. This is not science fiction. This is the mystery we are about to unravel. For centuries, scientists, philosophers, and dreamers have searched for the hidden patterns that might govern the universe. From the spirals of galaxies to the tiniest particles, there are whispers of order in the chaos. Today, we dive into 30 mind-bending theories that explore these cosmic secrets. Theories that challenge what we know about space, time, and reality itself. Stay with us because by the end of this journey, you might just see the universe in a whole new light. Ready to uncover the hidden patterns of the cosmos? Let's begin. Now, let's take a closer look at the first theory, one that reveals a stunning connection between mathematics and the natural world. The Fibonacci sequence, a series of numbers where each number is the sum of the two preceding ones, shows up in the most unexpected places. From the spirals of galaxies to the arrangement of leaves on a stem, this pattern seems to be woven into the fabric of the universe itself. Consider the spiral arms of galaxies like the Milky Way. Their structure often mirrors the Fibonacci sequence, creating a mesmerizing symmetry that feels almost intentional. Even hurricanes with their swirling winds follow this same spiral pattern, as if nature itself is following a mathematical blueprint, but it doesn't stop there. Look at a sunflower and you'll see its seeds arranged in perfect Fibonacci spirals. Pine cones, pineapples, and even the branching of trees all echo this sequence. It's as if the universe has a favorite formula and it's using it everywhere. So, is this just a coincidence, or is there something deeper at play? Some scientists argue that the Fibonacci sequence emerges naturally from the way living things grow and evolve, optimizing space and efficiency. Others suggest it might hint at a universal design, a hidden order that governs everything from the smallest plant to the largest galaxy. What's fascinating is that this pattern isn't just limited to Earth. It appears across the cosmos, suggesting that the Fibonacci sequence might be a fundamental part of how the universe organizes itself. Could this be evidence of a hidden mathematical language written into the stars? As we move forward, keep this idea in mind. The Fibonacci sequence is just the beginning of our journey into the universe's hidden patterns. Next, we'll explore how the echoes of the Big Bang itself might hold clues to the cosmos's deepest secrets. Now, let's shift our gaze from the spirals of galaxies to something far more ancient, a faint whisper from the dawn of time itself. The cosmic microwave background, or CMB, is often described as the afterglow of the Big Bang. It's the oldest light in the universe, a snapshot of what the cosmos looked like just 380,000 years after its explosive birth. Imagine the universe as a newborn, still glowing with the heat of its creation. As it expanded and cooled, this light stretched into microwaves, creating a faint glow that permeates every corner of space. Today, we can detect this glow as a nearly uniform background radiation. But hidden within it are tiny fluctuations, patterns that tell a story about the universe's infancy. These patterns are like cosmic fingerprints, revealing the seeds of everything we see today. The Wilkinson Microwave Anisotropy Probe, or WMAP, was a groundbreaking mission designed to map these fluctuations with incredible precision. What it found was astonishing. The CMB isn't perfectly smooth, it's dotted with tiny variations in temperature, some warmer, some cooler. These variations are the imprints of density fluctuations in the early universe, the very regions that would later grow into galaxies, stars, and planets. But what do these patterns mean? Scientists believe they hold clues to the universe's origins and structure. The distribution of these fluctuations suggests that the early universe was filled with a kind of cosmic symphony, sound waves rippling through the hot, dense plasma. These waves left behind a signature, a pattern that WMAP and other missions have been able to decode. What's even more intriguing is that these patterns align with predictions made by the Big Bang theory. They provide strong evidence that our universe began in a hot, dense state and has been expanding ever since. But they also raise new questions. Why do these patterns look the way they do? Could they hint at even deeper truths about the nature of space and time? As we continue to study the CMB, we're not just looking back in time, we're uncovering the blueprint of the universe itself. These subtle patterns are a reminder that even the faintest whispers can carry profound truths. And with that, let's turn our attention to another fascinating idea: fractals, and how they might reveal the universe's hidden geometry. Now, let's take a step into a world where patterns repeat themselves endlessly, revealing a hidden order that seems to echo across the cosmos. Fractals, those mesmerizing, self-repeating shapes, are everywhere, from the jagged edges of coastlines to the branching veins of a leaf. But what if these intricate patterns aren't just confined to Earth? What if the universe itself is a fractal, a vast, repeating structure that stretches across unimaginable scales? Fractals are mathematical wonders, shapes that look similar no matter how much you zoom in or out. Think of a snowflake. Each tiny branch mirrors the larger structure, creating a pattern that feels infinite. This self-similarity isn't just beautiful, it's a clue to something deeper. Scientists have found fractal-like patterns in the distribution of galaxies, where clusters of stars form webs that resemble the branching of trees or the flow of rivers. But how does this connect to the universe as a whole? Some theories suggest that the cosmos might operate like a fractal, with structures repeating at different scales. Imagine zooming out from a galaxy cluster and finding that the entire universe mirrors the same patterns on a grander scale. This idea challenges our understanding of space and time, proposing that the universe might not be random but instead governed by a hidden, repeating order. One of the most fascinating aspects of fractals is their infinite complexity. Unlike simple shapes, fractals never truly end. They keep revealing new layers of detail the closer you look. This has led some researchers to wonder if the universe itself could be infinitely complex, with patterns repeating endlessly across space and time. Could the galaxies we see be just one layer of a much larger, fractal-like structure? Of course, this idea is still speculative, but it opens up exciting possibilities. If the universe is a fractal, it could mean that the patterns we observe, from the smallest particles to the largest galaxy clusters, are all connected by a single, underlying principle. This would revolutionize our understanding of reality, suggesting that the cosmos is far more interconnected than we ever imagined. As we ponder the fractal nature of the universe, we're reminded that even the most familiar patterns can hold profound mysteries. From the spirals of galaxies to the branching of trees, fractals invite us to see the world and the cosmos in a whole new way. And with that, let's turn our attention to another intriguing idea: the golden ratio and its mysterious presence in the fabric of the universe. Now, let's shift our gaze to a number that has fascinated mathematicians, artists, and scientists for centuries: the golden ratio. Often represented by the Greek letter phi, this special number, approximately 1.618, appears in everything from the spirals of seashells to the proportions of the human body. But what if this ratio isn't just a quirk of nature on Earth? What if it's woven into the very fabric of the cosmos itself? Take spiral galaxies, for example. These majestic structures, with their swirling arms of stars and gas, often exhibit a striking resemblance to the logarithmic spirals found in nature, spirals that follow the golden ratio. The famous Whirlpool galaxy, for instance, showcases arms that expand outward in a way that mirrors this mathematical proportion. Could this be a coincidence, or is it a hint of a deeper, universal pattern? The golden ratio doesn't stop at galaxies. It also seems to play a role in the way planets and moons orbit their stars. Some researchers have noted that the distances between planetary orbits in our solar system align surprisingly well with the golden ratio. Even the proportions of celestial bodies, like the size of Saturn's rings relative to the planet itself, appear to reflect this ratio, but here's where the debate begins. Is the golden ratio's presence in the cosmos evidence of a universal design, a kind of cosmic blueprint that governs the structure of the universe, or is it simply a case of humans seeing patterns where none exist? After all, the universe is vast and varied, and with so many shapes and structures, it's possible that some will naturally align with the golden ratio purely by chance. Supporters of the universal design theory argue that the golden ratio's prevalence across different scales, from the microscopic to the cosmic, suggests a fundamental principle at work. They point to its appearance in everything from the arrangement of leaves on a stem to the spiral arms of galaxies as evidence of a hidden order. Skeptics, on the other hand, caution against overinterpreting these patterns, noting that the universe is full of randomness and that the golden ratio might just be one of many mathematical relationships that emerge naturally. As we explore this intriguing idea, it's worth asking, if the golden ratio truly is a universal constant, what does that mean for our understanding of the cosmos? Could it be a clue to the underlying laws that govern everything from the smallest particles to the largest galaxies? Or is it simply a beautiful coincidence, a reminder of the elegance and mystery that permeate the universe? With these questions in mind, let's turn our attention to another captivating theory, one that takes us beyond the boundaries of our own universe and into the realm of the multiverse. Now, let's venture beyond the boundaries of our own universe and into the mind-bending realm of the multiverse. Imagine, if you will, that our universe is just one of countless others, each with its own unique set of physical laws and constants. This is the essence of the multiverse theory, a concept that suggests the cosmos is far more vast and varied than we could ever imagine. In this framework, the patterns we observe in our universe, like the golden ratio or the cosmic web, might be just one possibility among an infinite array of configurations. In some universes, gravity could be stronger or weaker, the speed of light might vary, or even the fundamental particles that make up matter could be entirely different. The implications are staggering. What we consider normal or universal might simply be a product of the specific conditions in our corner of existence. But how does this relate to hidden patterns? If the multiverse exists, it raises the possibility that the patterns we see in our universe are not universal truths but rather local phenomena. For example, the Fibonacci sequence or the golden ratio might be common in our universe because of the specific laws that govern it. But in another universe, entirely different mathematical relationships could dominate. This idea challenges us to rethink what we consider fundamental or inevitable about the cosmos. Supporters of the multiverse theory argue that it provides a natural explanation for the fine-tuning of our universe. Why do the constants of nature seem perfectly calibrated to allow for life? In a multiverse, it's possible that every conceivable combination of physical laws exists somewhere, and we just happen to live in a universe where those laws permit our existence. Skeptics, however, question whether the multiverse is more philosophy than science, as it's currently impossible to observe or test these other universes directly. Yet, the multiverse theory also opens up fascinating questions about hidden patterns. Could there be overarching principles that apply across all universes, even if their specific laws differ? Some theorists suggest that certain mathematical or geometric patterns might be universal, transcending the boundaries of individual universes. Others propose that the multiverse itself might have a structure, with universes arranged in a higher dimensional landscape governed by its own hidden rules. As we ponder these ideas, it's worth considering what the multiverse means for our search for meaning and understanding. If our universe is just one among many, does that diminish its significance, or does it make the patterns we discover here even more remarkable? And if hidden patterns exist across the multiverse, what might they tell us about the nature of reality itself? With these questions lingering, let's turn our attention to another intriguing theory, one that suggests the universe might not be as three-dimensional as it seems. Now, let's take a step into a theory that challenges our very perception of reality, the holographic principle. Imagine for a moment that everything you see, touch, and experience in the three-dimensional world around you is actually a projection of information encoded on a two-dimensional surface. Sounds like science fiction, right? But this is the core idea behind the holographic principle, a theory that suggests our universe might be a hologram. At its heart, the holographic principle proposes that all the information needed to describe our three-dimensional universe could be stored on a two-dimensional boundary, much like how a hologram works. In a hologram, a flat surface contains all the data required to create a three-dimensional image when light shines on it. Similarly, this theory suggests that the patterns and structures we observe in the cosmos, galaxies, stars, even ourselves, might be projections of information encoded on a distant two-dimensional surface. But how does this connect to hidden patterns? If the universe is indeed a hologram, then the patterns we see, like the cosmic web or the Fibonacci sequence, might not be fundamental truths of reality, but rather manifestations of deeper, hidden information. Think of it like watching a movie on a screen. The images you see are projections of data stored on a film reel or a digital file. In the same way, the holographic principle suggests that the universe's patterns are projections of a more fundamental layer of reality, one that we can't directly perceive. This idea has profound implications for our understanding of space, time, and even the nature of information itself. For instance, it could explain why the universe appears to have a maximum amount of information it can contain, much like a hologram has a limit to the detail it can display. It also raises questions about the nature of black holes. Some physicists have suggested that the information swallowed by a black hole isn't lost but is instead encoded on its event horizon, the two-dimensional boundary surrounding it. Supporters of the holographic principle argue that it could provide a unified framework for understanding gravity and quantum mechanics, two areas of physics that have proven notoriously difficult to reconcile. Skeptics, however, point out that the theory is still largely speculative and lacks direct experimental evidence. Yet, the idea continues to captivate scientists and thinkers alike, offering a tantalizing glimpse into the possibility that our universe is far stranger than it appears. So, what does this mean for hidden patterns? If the holographic principle is correct, then the patterns we observe in the cosmos might be like shadows on a cave wall, hints of a deeper, more complex reality that lies beyond our perception. It challenges us to rethink not just what we see, but how we see it. Are the laws of physics and the structures of the universe truly fundamental, or are they just the surface-level manifestations of something far more intricate? As we ponder this mind-bending theory, let's shift our focus to another fascinating idea, one that explores whether the universe's hidden patterns might be the result of a cosmic designer. Now, let's turn our attention to a theory that has sparked some of the most profound debates in science and philosophy, the fine-tuning problem. Imagine the universe as a vast, intricate machine with countless dials and settings. Each of these settings represents a fundamental constant, like the strength of gravity or the mass of an electron. What's astonishing is that if even one of these constants were slightly different, life as we know it might not exist. This is the essence of the fine-tuning problem, the idea that the universe's fundamental constants appear to be precisely calibrated to allow for the existence of life. Take gravity, for example. If the force of gravity were just a tiny bit stronger, stars would burn out too quickly, leaving no time for planets to form or life to evolve. If it were weaker, stars might not ignite at all, leaving the universe cold and dark. Similarly, the mass of an electron is finely balanced to allow atoms to form stable structures. If it were even slightly different, the chemical reactions necessary for life might never occur. These are just a few examples, but the list goes on. Each fundamental constant seems to be set just right, as if the universe were designed with life in mind. This raises a fascinating question. Is this fine-tuning evidence of a hidden pattern, or could it point to something even more profound, a cosmic designer? Some scientists and thinkers argue that the fine-tuning of the universe suggests the existence of a multiverse. In this view, our universe is just one of countless others, each with its own set of physical constants. In most of these universes, the constants are not conducive to life, but in ours, they happen to be just right. According to this perspective, the fine-tuning isn't the result of design, but rather a statistical inevitability, a cosmic lottery win. On the other hand, some propose that the fine-tuning of the universe might indicate the presence of a higher intelligence or a cosmic designer. This idea, often referred to as the anthropic principle, suggests that the universe's constants are the way they are because they allow for the existence of observers like us. In other words, the universe seems fine-tuned for life because, well, we're here to observe it. This perspective doesn't necessarily point to a specific designer, but raises the possibility that the universe's patterns are not random but intentional. Of course, not everyone agrees. Skeptics argue that the fine-tuning problem might simply reflect our limited understanding of the universe's laws. Perhaps there's a deeper, yet-to-be-discovered principle that explains why the constants are what they are, without invoking a multiverse or a designer. After all, science has a history of uncovering hidden patterns that initially seemed mysterious or coincidental. So, what does this mean for hidden patterns? If the universe is finely tuned, whether by chance, necessity, or design, it suggests that the patterns we observe, from the structure of atoms to the formation of galaxies, are not arbitrary. They might be the result of a deeper, underlying order, one that we're only beginning to understand. The fine-tuning problem challenges us to consider whether the universe's patterns are the product of random chance, a multiverse, or something even more extraordinary. As we reflect on this intriguing theory, let's move forward to explore another captivating idea, one that examines the large-scale structure of the universe and how its patterns might reveal the secrets of cosmic evolution. Now, let's shift our gaze to the grand tapestry of the cosmos, the large-scale structure of the universe. Picture the universe not as a random scattering of stars and galaxies, but as an intricate web, a vast network of galaxies, dark matter, and cosmic voids. This structure, often referred to as the cosmic web, is one of the most striking patterns we've discovered in the universe, and it holds profound clues about how the cosmos evolved over billions of years. At its core, the cosmic web is a network of filaments made up of galaxies and dark matter, stretching across unimaginable distances. These filaments intersect at dense nodes where galaxy clusters, some of the largest structures in the universe, reside. Between these filaments lie vast, empty regions known as cosmic voids, areas where matter is sparse and galaxies are few and far between. This web-like structure isn't just a random arrangement. It's a direct result of the universe's early conditions and the forces that have shaped it over time. To understand how this cosmic web formed, we need to go back to the very beginning, the Big Bang. In the early universe, matter was distributed almost uniformly, but tiny fluctuations in density existed. These fluctuations, amplified by gravity over billions of years, caused matter to clump together, forming the seeds of galaxies and galaxy clusters. As gravity continued to pull matter into these dense regions, the spaces between them grew emptier, creating the voids we see today. The result is a universe that resembles a sponge, with dense filaments and clusters surrounded by vast, empty spaces. But the cosmic web isn't just a relic of the past, it's a dynamic structure that continues to evolve. Dark matter, the mysterious substance that makes up about 85% of the universe's mass, plays a crucial role in shaping this web. Although invisible, dark matter's gravitational pull guides the movement of galaxies and gas, weaving the filaments of the cosmic web ever tighter. Meanwhile, dark energy, the force driving the universe's accelerated expansion, stretches the web on even larger scales, influencing how galaxies move and cluster over time. What makes the cosmic web so fascinating is that it's not just a pattern, it's a map of the universe's history. By studying the distribution of galaxies and the structure of the web, scientists can trace the evolution of the universe from its earliest moments to the present day. For example, the way galaxies cluster along filaments can reveal how dark matter is distributed, while the size and shape of voids can tell us about the influence of dark energy. In this way, the cosmic web acts as a cosmic fingerprint, encoding the story of the universe's growth and transformation. But the cosmic web also raises intriguing questions. Why does the universe have this particular structure? Could there be other, even larger patterns hidden within the web? Some theories suggest that the cosmic web might be part of an even grander design, one that connects the universe's largest structures to its smallest particles. Others propose that the web's structure could hint at the nature of dark matter and dark energy, two of the greatest mysteries in modern science. As we unravel the secrets of the cosmic web, we're not just exploring the universe's structure, we're uncovering the hidden patterns that govern its evolution. From the tiniest fluctuations in the early universe to the vast, interconnected network we see today, the cosmic web reminds us that the universe is far more than a collection of random objects. It's a dynamic, evolving system shaped by forces we're only beginning to understand. With this in mind, let's turn our attention to another fascinating theory, one that explores the mysterious connections between particles across vast distances, and how these connections might reveal a hidden layer of interconnectedness in the universe. Now, let's dive into a phenomenon that seems to defy our everyday understanding of reality: quantum entanglement. Imagine two particles separated by vast distances, yet somehow connected in a way that allows them to influence each other instantaneously. This strange and fascinating behavior, known as quantum entanglement, suggests that the universe might be far more interconnected than we ever imagined. At its core, quantum entanglement occurs when two or more particles become linked in such a way that the state of one particle directly affects the state of the other, no matter how far apart they are. For example, if one particle is measured and found to have a specific property like spin or polarization, its entangled partner will instantly exhibit a corresponding property, even if it's on the other side of the galaxy. This connection happens faster than the speed of light, challenging our classical notions of space and time. Albert Einstein famously referred to this phenomenon as spooky action at a distance, expressing his discomfort with the idea that particles could communicate instantaneously across vast distances. Yet, decades of experiments have confirmed that entanglement is real, and it's one of the most well-established principles in quantum mechanics. These experiments have shown that entangled particles remain connected, even when separated by thousands of kilometers, suggesting that the universe operates on rules that are far stranger than we once thought. But what does this mean for our understanding of the universe? Some scientists believe that entanglement hints at a deeper, hidden layer of reality, a level of interconnectedness that we're only beginning to grasp. This interconnectedness might not be limited to particles. It could extend to larger systems or even the universe as a whole. In this view, the universe isn't just a collection of separate objects, but a vast, entangled network where everything is subtly linked. One intriguing idea is that entanglement could be the key to understanding the fabric of spacetime itself. Some theories propose that spacetime emerges from the entanglement of quantum particles, suggesting that the connections we observe at the quantum level might be the building blocks of the universe's structure. If this is true, then entanglement isn't just a curious quirk of quantum mechanics. It's a fundamental feature of reality, shaping everything from the smallest particles to the largest cosmic structures. Another fascinating aspect of entanglement is its potential role in the universe's evolution. Some researchers speculate that entanglement might have played a crucial role in the early universe, helping to synchronize the properties of particles and set the stage for the formation of galaxies and other large-scale structures. If so, then the hidden connections we observe today might be echoes of processes that shaped the cosmos billions of years ago. Of course, entanglement also raises profound questions. How do particles remain connected across such vast distances? What mechanism allows them to communicate instantaneously? And could this interconnectedness extend beyond the quantum world, influencing the behavior of larger systems or even living organisms? While we don't yet have all the answers, these questions remind us that the universe is full of mysteries waiting to be unraveled. As we explore the implications of quantum entanglement, we're not just studying the behavior of particles, we're peering into the hidden layers of reality itself. From the strange connections between entangled particles to the possibility of a deeply interconnected universe, entanglement challenges us to rethink our understanding of space, time, and the very nature of existence. With this in mind, let's turn our attention to another intriguing theory, one that examines the idea that the universe's patterns are the way they are because they allow for the existence of observers like us. Now, shifting our focus to a theory that bridges the gap between science and philosophy, we arrive at the anthropic principle. This intriguing idea suggests that the universe's patterns and physical constants are precisely tuned to allow for the existence of observers like us. In other words, the conditions of the universe are not random. They seem to be finely balanced to support life, raising profound questions about why this is the case. At its core, the anthropic principle comes in two main forms. The first, known as the weak anthropic principle, simply states that the universe must be compatible with the existence of observers because, well, we're here to observe it. This version doesn't claim any deeper meaning. It's more of a logical observation. For example, if the universe had different physical constants like a stronger or weaker gravitational force, life as we know it might not have emerged. The fact that we exist means the universe must have the right conditions for us to exist. The second form, the strong anthropic principle, takes this idea further. It proposes that the universe must have properties that allow life to develop at some point in its history. This version often sparks debate as it implies a kind of purpose or design behind the universe's structure. Some interpret this as evidence of a cosmic designer, while others see it as a natural consequence of the laws of physics. But is the anthropic principle a scientific principle, or is it more of a philosophical stance? On one hand, it's grounded in observable facts like the precise values of physical constants that make life possible. On the other hand, it raises questions that science alone can't fully answer, such as why these constants have the values they do. This has led some to argue that the anthropic principle is more of a philosophical framework than a testable scientific theory. Critics of the anthropic principle often point out that it can seem like a circular argument. Saying the universe is the way it is because we exist doesn't necessarily explain why it's that way in the first place. However, supporters argue that it provides a useful perspective for understanding the unique conditions of our universe, especially when combined with other theories like the multiverse. If there are countless universes with different physical constants, it's not surprising that at least one of them would have the right conditions for life, and that's the one we find ourselves in. The anthropic principle also invites us to consider our place in the cosmos. If the universe is finely tuned for life, does that mean life is a rare and special phenomenon, or is it an inevitable outcome of the universe's structure? And if life is so central to the universe's design, what does that say about the nature of reality itself? As we ponder these questions, it's clear that the anthropic principle sits at the intersection of science and philosophy, challenging us to think deeply about the nature of existence. Whether it's seen as a scientific insight or a philosophical reflection, It reminds us that the universe is not just a random collection of particles, it's a place where life and the ability to observe and understand it is possible. With this in mind, let's turn our attention to another mysterious force shaping the universe: dark matter and dark energy, and how their hidden nature might hold the key to understanding cosmic patterns. Now, as we venture deeper into the mysteries of the cosmos, we encounter two of the most enigmatic forces in the universe: dark matter and dark energy. These invisible components make up the vast majority of the universe's content, yet they remain shrouded in mystery. Together, they shape the very fabric of space and time, influencing everything from the formation of galaxies to the accelerating expansion of the universe. But what exactly are they, and how do they contribute to the hidden patterns we observe? Let's start with dark matter. Unlike ordinary matter, which makes up stars, planets, and everything we can see, dark matter doesn't emit, absorb, or reflect light. It's completely invisible, yet its presence is undeniable. How do we know it exists? The answer lies in its gravitational effects. For instance, galaxies rotate at speeds that would cause them to fly apart if only the visible matter were holding them together. Something unseen, dark matter, must be providing the extra gravitational pull to keep them intact. This invisible scaffolding not only holds galaxies together, but also shapes the large-scale structure of the universe, forming a cosmic web that connects galaxy clusters across vast distances. But dark matter is only half the story. Enter dark energy, an even more mysterious force that makes up about 68% of the universe. Unlike dark matter, which pulls things together through gravity, dark energy pushes the universe apart. It's the driving force behind the accelerating expansion of the universe, a discovery that shocked scientists in the late 1990s. Before then, it was widely believed that the universe's expansion was slowing down due to gravity. Instead, observations of distant supernova revealed that the expansion is speeding up, propelled by an unknown energy that permeates space itself. So, what could dark energy be? One leading idea is that it's a property of space itself, often referred to as the cosmological constant. This concept, first proposed by Albert Einstein, suggests that empty space isn't truly empty. It has an inherent energy that causes it to expand. Another possibility is that dark energy is a dynamic field, changing over time and interacting with the universe in ways we don't yet understand. Whatever it is, its effects are profound, shaping the fate of the cosmos on the grandest scales. Together, dark matter and dark energy form the backbone of the universe's structure and evolution. Dark matter's gravitational influence pulls matter together, forming galaxies and clusters, while dark energy's repulsive force drives the universe's expansion, pushing galaxies apart over time. This delicate balance between attraction and repulsion has sculpted the universe into the intricate patterns we see today. But here's the catch: despite their overwhelming presence, we still don't know what dark matter and dark energy actually are. Are they new forms of matter and energy, or do they point to a deeper, hidden layer of physics that we've yet to uncover? Some scientists believe that understanding these mysterious components could unlock the secrets of the universe's hidden patterns. For example, the distribution of dark matter in the cosmic web might reveal clues about the early universe and the processes that shaped it. Similarly, unraveling the nature of dark energy could help us predict the ultimate fate of the cosmos. Will it continue expanding forever, or will it eventually collapse back in on itself? As we grapple with these questions, one thing is clear: dark matter and dark energy are not just footnotes in the story of the universe, they are central characters. They remind us that what we see is only a tiny fraction of what's out there, and that the universe is far more complex and mysterious than we can imagine. With every discovery, we inch closer to understanding these hidden forces, but the journey is far from over. With this in mind, let's turn our attention to another cornerstone of cosmic history: the Big Bang and the initial conditions that set the stage for the universe's evolution. Now, as we shift our focus to the very beginning of everything, let's explore the Big Bang and the initial conditions that laid the foundation for the universe as we know it. The Big Bang isn't just a moment in time, it's the starting point of all space, time, and matter. But what exactly happened in those first moments, and how did they shape the hidden patterns we see today? Imagine the universe as a blank canvas. The Big Bang was the first stroke of the brush, setting everything into motion. In the tiniest fraction of a second, the universe expanded faster than the speed of light, a process known as inflation. This rapid expansion smoothed out the early universe, creating a nearly uniform distribution of energy. But within that uniformity, tiny fluctuations existed, imperfections so small they were almost insignificant. Yet, these fluctuations were the seeds of everything we see today. These initial conditions weren't random. They were governed by the laws of physics, which dictated how energy and matter would behave as the universe cooled and expanded. For example, the slight variations in density caused by those early fluctuations led to the formation of galaxies, stars, and planets. Without those subtle differences, the universe might have remained a featureless void. Instead, they gave rise to the intricate cosmic web of galaxies and clusters we observe today. But here's the question: were these initial conditions predetermined, or were they the result of chance? Some scientists argue that the laws of physics themselves dictated the outcome, making the universe's structure inevitable. Others suggest that the early universe was a chaotic place, where random quantum fluctuations played a significant role in shaping its future. This debate touches on one of the deepest mysteries in science: whether the universe is governed by strict laws or if randomness plays a fundamental role. One clue lies in the cosmic microwave background, the afterglow of the Big Bang. This faint radiation carries imprints of the early universe, revealing the density variations that eventually grew into galaxies. By studying these patterns, scientists can piece together the conditions of the early universe and test theories about its origins. For instance, the precise measurements of the cosmic microwave background support the idea of inflation, suggesting that the universe's expansion was not random but driven by a specific set of physical processes. Yet, even with this evidence, the question of whether the initial conditions were predetermined or random remains unanswered. Some theories propose that our universe is just one of many in a multiverse, each with its own set of initial conditions. In this view, the patterns we observe might be the result of chance. Our universe simply happens to have the right conditions for galaxies, stars, and life to exist. Others believe that the initial conditions were finely tuned, pointing to a deeper, perhaps even intentional, design. What's clear is that the Big Bang and its initial conditions are central to understanding the universe's hidden patterns. They set the stage for everything that followed, from the formation of the first atoms to the emergence of complex structures like galaxies and black holes. By studying these early moments, we gain insight into not only how the universe began, but also how it evolved into the intricate, interconnected cosmos we see today. As we continue to unravel the mysteries of the Big Bang, we're reminded that the universe's story is still being written. Each discovery brings us closer to understanding the forces that shaped its beginnings and the patterns that define its present. And with that, let's turn our attention to another fascinating theory, the simulation hypothesis, which suggests that our universe might be a programmed reality. Now, let's take a step into one of the most mind-bending theories of all, the simulation hypothesis. What if everything we see, touch, and experience is nothing more than an incredibly advanced simulation created by beings far beyond our understanding? This idea, once the stuff of science fiction, has gained serious traction among scientists, philosophers, and even tech entrepreneurs. But what exactly does it mean for our universe to be a simulation, and could there be evidence to support such a claim? At its core, the simulation hypothesis suggests that our reality is not the base layer of existence but rather a programmed construct, much like a highly sophisticated video game. In this scenario, the laws of physics, the patterns we observe in the cosmos, and even our own consciousness could be the result of code written by an advanced civilization. Think of it this way: if humans can create virtual worlds with their own rules and logic, why couldn't a more advanced species do the same on a cosmic scale? One of the most compelling arguments for the simulation hypothesis comes from the idea of technological advancement. As our own computing power grows exponentially, we're already creating simulations that mimic reality with stunning accuracy. From weather models to virtual reality environments, we're getting closer to building worlds that feel real to their inhabitants. If this trend continues, it's not hard to imagine a future where entire universes could be simulated. And if that's possible, then the odds that we're living in the original, base reality start to look slim. But what about evidence? Some scientists point to the strange behavior of particles at the quantum level as a potential clue. For example, particles don't seem to have definite properties until they're observed, almost as if the universe is rendering details only when needed, a feature that could be explained by a simulation conserving computational resources. Others point to the mathematical nature of the universe itself. The fact that the cosmos can be described so precisely by equations might suggest that it's built on a framework of code. On the other hand, critics argue that the simulation hypothesis is more philosophy than science. Without direct evidence, it's impossible to prove or disprove. Some also question why an advanced civilization would bother simulating an entire universe, let alone one with so much suffering and chaos. Couldn't they create a more perfect, harmonious reality? These questions highlight the speculative nature of the theory, but they don't necessarily rule it out. Another angle to consider is the possibility of glitches or errors in the simulation. If our universe is a programmed reality, there might be moments where the code shows through anomalies that defy explanation. Some have suggested that déjà vu, strange coincidences, or even unexplained phenomena like UFOs could be signs of such glitches. While these ideas are intriguing, they remain firmly in the realm of speculation. Ultimately, the simulation hypothesis challenges us to rethink our understanding of reality. Whether or not it's true, it raises profound questions about the nature of existence, consciousness, and the universe itself. Could the patterns we observe in the cosmos be the result of a grand design, or are they simply the output of an unimaginably complex program? As we continue to explore this theory, we're reminded that the universe is full of mysteries waiting to be unraveled. With that in mind, let's turn our attention to another fascinating concept: the role of symmetry in physics, and how it might reveal deeper, hidden patterns governing the universe. Now let's shift our gaze to a concept that lies at the very heart of physics: symmetry. Symmetry isn't just about beauty or balance. It's a fundamental principle that seems to underpin the very fabric of the universe. From the way particles interact to the grand structures of galaxies, symmetry plays a crucial role in shaping the laws of nature. But what does symmetry really mean in the context of physics? And how might it reveal deeper, hidden patterns governing our reality? At its simplest, symmetry refers to a kind of balance or invariance, a property that remains unchanged even when something else changes. For example, think of a snowflake. No matter how you rotate it, it looks the same. This is a visual symmetry, but in physics, symmetries are far more profound. They describe how the laws of nature remain consistent under certain transformations, like moving through space, traveling through time, or even flipping the direction of particles. These symmetries aren't just abstract ideas, they're the foundation of some of the most important principles in science. One of the most famous examples is the conservation of energy. This principle states that energy cannot be created or destroyed, it can only change forms. But why is energy conserved? The answer lies in symmetry. Specifically, it's tied to the idea that the laws of physics don't change over time. If you perform an experiment today and repeat it tomorrow, the results should be the same. This symmetry, called time translation symmetry, ensures that energy is conserved. In other words, the hidden pattern here is that the universe's laws are timeless, and this timelessness gives rise to the conservation of energy. But symmetry doesn't stop there. It also plays a key role in the behavior of particles and forces. Take the standard model of particle physics, for instance. This framework describes how fundamental particles interact through forces like electromagnetism and the strong nuclear force. At the heart of the standard model are mathematical symmetries that dictate how particles can transform into one another and how forces are mediated. These symmetries are so precise that they've allowed scientists to predict the existence of particles before they were even discovered, like the Higgs boson. Another fascinating example is the concept of gauge symmetry, which governs the behavior of forces like electromagnetism. Gauge symmetry ensures that the equations describing these forces remain consistent, no matter how you tweak certain parameters. This might sound abstract, but it's what allows electric and magnetic fields to interact in predictable ways, powering everything from your smartphone to the stars in the sky. Without these symmetries, the universe as we know it simply wouldn't function. So, what does all this tell us about hidden patterns in the universe? Symmetry suggests that beneath the apparent chaos and complexity of the cosmos, there's an underlying order, a set of rules that remain constant no matter where or when you look. These symmetries aren't just mathematical curiosities, they're the scaffolding upon which the universe is built. They hint at a deeper reality, one where the patterns we observe are the result of fundamental principles that transcend space and time. But here's the intriguing part: sometimes symmetries can be broken. For example, in the early universe, the forces of nature were unified under a single, symmetrical framework. As the universe cooled, this symmetry broke, giving rise to the distinct forces we see today. This process, known as symmetry breaking, is thought to have shaped the structure of the universe, from the formation of galaxies to the diversity of particles. It's as if the universe started with a perfect symmetry and then, through a series of cosmic events, unfolded into the complex, asymmetrical world we inhabit. This raises a profound question. If symmetry is so fundamental, why isn't the universe perfectly symmetrical? The answer might lie in the interplay between symmetry and asymmetry. Just as a snowflake's beauty comes from its intricate patterns, the universe's richness may arise from the tension between symmetry and its breaking. This duality could be the key to understanding the hidden patterns that govern everything from the smallest particles to the largest structures in the cosmos. As we continue to explore the role of symmetry in physics, we're reminded that the universe is not just a collection of random events, but a tapestry woven with threads of order and balance. Whether it's the conservation of energy, the behavior of particles, or the evolution of the cosmos, symmetry offers a glimpse into the deeper, hidden patterns that shape our reality. And with that, let's turn our attention to another captivating idea: the butterfly effect and chaos theory, and how they challenge our understanding of order and predictability in the universe. Now, let's dive into a concept that turns our understanding of order on its head: the butterfly effect and chaos theory. Imagine a butterfly flapping its wings in Brazil, setting off a chain of events that leads to a tornado in Texas. This idea, often used to illustrate chaos theory, suggests that even the tiniest changes in initial conditions can lead to dramatically different outcomes over time. But what does this mean for the universe's hidden patterns? Does chaos defy order, or could it be hiding a deeper kind of structure beneath the surface? At its core, chaos theory explores how systems that appear random or unpredictable can actually be governed by underlying rules. These systems are highly sensitive to their starting conditions, meaning that even a minuscule change like the flap of a butterfly's wings can ripple through the system and produce wildly different results. This sensitivity makes long-term prediction nearly impossible, even in systems that are deterministic, meaning they follow strict laws of cause and effect. Weather is a classic example. Despite our advanced technology, forecasting the weather more than a few days in advance remains a challenge because of the countless variables involved and their sensitivity to initial conditions. But here's where it gets fascinating. While chaotic systems seem unpredictable, they're not entirely random. They operate within certain boundaries, often following patterns called strange attractors. These are like invisible blueprints that guide the system's behavior, even if the exact path it takes is impossible to predict. Think of it like a river flowing through a canyon. The water's path might twist and turn unpredictably, but it's still confined by the canyon walls. In the same way, chaotic systems have an underlying structure that keeps them from spiraling into complete disorder. So, does chaos theory reveal hidden patterns, or does it prove that the universe is fundamentally unpredictable? The answer might be a bit of both. On one hand, chaos highlights the limits of our ability to predict certain systems, especially those with many interacting variables. On the other hand, it suggests that even within apparent randomness, there's an underlying order, a kind of hidden geometry that shapes how systems evolve. This duality challenges us to rethink what we mean by patterns. Perhaps the universe's hidden patterns aren't always neat and predictable, but instead emerge from the interplay of order and chaos. One of the most intriguing aspects of chaos theory is its connection to the concept of emergence. Emergence refers to how complex systems and patterns can arise from simple rules. For example, a flock of birds might follow basic rules about spacing and direction, yet the overall movement of the flock appears intricate and coordinated. Similarly, chaotic systems can give rise to complex, beautiful patterns that seem to defy their unpredictable nature. This raises the question, could the universe itself be a kind of emergent system, with its vast structures and phenomena arising from simple, chaotic beginnings? As we explore the butterfly effect and chaos theory, we're reminded that the universe is full of surprises. What seems like randomness might be hiding a deeper kind of order, one that's not always easy to see or predict. This tension between chaos and order could be the key to understanding some of the universe's most profound mysteries. And with that, let's turn our attention to another captivating idea: the role of time in cosmic patterns, and how the arrow of time might influence the emergence of order in the universe. Now, let's shift our focus to a dimension that shapes everything we observe: time. Time is more than just a measure of moments passing. It's a fundamental force that influences the very fabric of the universe. From the arrow of time to the expansion of the cosmos, time plays a crucial role in how patterns emerge and evolve. But could time itself be a hidden variable, quietly guiding the universe's hidden order? The concept of the arrow of time is central to understanding how patterns form. Unlike space, which we can move through in any direction, time flows in one direction forward. This unidirectional flow creates a sense of order from the past to the present and into the future. It's why we remember yesterday but not tomorrow, and why broken eggs don't reassemble themselves. This arrow of time is deeply tied to the second law of thermodynamics, which states that entropy or disorder always increases over time. As the universe expands and entropy grows, it drives the formation of structures and patterns, from galaxies to life itself. But here's where it gets intriguing. While time's arrow points forward, the universe's expansion adds another layer of complexity. As the cosmos stretches, it creates more space for matter and energy to interact, allowing patterns to emerge on ever larger scales. Think of it like a canvas that keeps growing, giving artists, or in this case, the laws of physics, more room to create. This expansion not only shapes the large-scale structure of the universe, like the cosmic web of galaxies, but also influences the smaller-scale patterns we see in stars, planets, and even the chemistry of life. Could time itself be a hidden variable subtly influencing these patterns? Some theories suggest that time might not be as straightforward as it seems. For instance, in quantum mechanics, time doesn't play the same role as it does in classical physics. At the quantum level, particles can exist in multiple states simultaneously, and their behavior isn't strictly bound by the arrow of time. This has led some scientists to propose that time might be an emergent property, arising from the interactions of countless particles rather than being a fundamental aspect of reality. If true, this would mean that time is not just a backdrop for the universe but a dynamic, evolving feature that shapes its patterns. Another fascinating idea is the possibility of time loops or cyclical time. In some cosmological models, the universe might go through endless cycles of expansion and contraction, with time repeating itself in each cycle. If this were the case, the patterns we observe today could be echoes of previous universes, hinting at a deeper, hidden order that transcends our current understanding of time. While this remains speculative, it challenges us to think of time not as a straight line but as a complex, multidimensional force. As we explore the role of time in cosmic patterns, we're reminded that time is more than just a ticking clock. It's a dynamic, evolving force that shapes the universe's structure and drives the emergence of order from chaos. Whether time is a hidden variable or an emergent property, its influence on the cosmos is undeniable. And with that, let's turn our attention to another captivating mystery: the search for extraterrestrial intelligence and how the quest for alien life might reveal hidden patterns in the universe. Now, let's venture into a realm that has captivated humanity for centuries: the search for extraterrestrial intelligence, or SETI. This quest isn't just about finding life beyond Earth. It's about uncovering whether the universe is teeming with life-supporting conditions, and if so, what hidden patterns might govern their existence. Could the search for alien life reveal a cosmic blueprint, a set of universal rules that make life not just possible, but perhaps inevitable? At the heart of SETI lies a profound question: are we alone in the universe? To answer this, scientists scan the skies for signals that might indicate the presence of intelligent life. But beyond the search for radio waves or laser pulses, SETI also explores the broader conditions that make life possible. For instance, the concept of the habitable zone around stars where temperatures are just right for liquid water to exist has become a cornerstone in the search for life. This zone isn't random, it's a pattern dictated by the laws of physics and chemistry, suggesting that life-supporting conditions might follow predictable rules across the cosmos. But what if life isn't confined to planets within these zones? Some theories propose that life could thrive in environments we once thought inhospitable, like the icy moons of Jupiter and Saturn, where subsurface oceans might harbor microbial life. If life can exist in such extreme conditions, it could mean that the universe is far more adaptable and perhaps far more alive than we ever imagined. This raises the possibility that life-supporting patterns aren't limited to Earth-like planets, but could be woven into the very fabric of the universe, appearing in unexpected places. Another intriguing angle is the idea of technosignatures, or signs of advanced civilizations. These could range from megastructures like Dyson spheres, hypothetical constructs designed to harness a star's energy, to atmospheric pollution on distant planets. Detecting such signatures wouldn't just prove the existence of alien life. It could reveal patterns of technological advancement and resource use that might be universal. Imagine discovering that civilizations across the galaxy follow similar paths of development, suggesting a shared cosmic trajectory. The search for extraterrestrial intelligence also ties into the broader question of whether life is a rare fluke or a common occurrence. If we find evidence of life elsewhere, it could imply that the universe is inherently life-friendly, with patterns and conditions that favor the emergence of living beings. On the other hand, if the search continues to come up empty, it might suggest that life is an extraordinary exception, shaped by a unique combination of factors. Either way, SETI offers a window into the hidden patterns that might govern the prevalence or scarcity of life in the cosmos. As we ponder the mysteries of SETI, we're reminded that the search for alien life isn't just about finding others, it's about understanding our place in the universe. Whether we discover a distant civilization or find ourselves alone, the patterns we uncover along the way will deepen our understanding of the cosmos and the forces that shape it. And with that, let's turn our gaze to another cosmic enigma, the role of black holes in shaping the universe's grand design. Now, let's shift our focus to one of the most enigmatic and powerful forces in the universe: black holes. These cosmic giants, often thought of as destructive voids, might actually play a crucial role in maintaining the universe's grand design. Far from being mere vacuum cleaners of space, black holes could be the architects of cosmic order, shaping galaxies and influencing the large-scale structure of the universe itself. At the center of nearly every galaxy, including our own Milky Way, lies a supermassive black hole. These colossal entities, with masses millions or even billions of times that of our Sun, exert an immense gravitational pull. But their influence goes far beyond just swallowing stars and gas. Supermassive black holes are thought to regulate the growth and behavior of galaxies. For instance, the energy released from matter falling into a black hole, known as accretion, can heat up surrounding gas, preventing it from cooling and forming new stars. This process effectively puts a brake on star formation, ensuring galaxies don't grow too quickly or chaotically. But black holes don't just limit growth, they also foster it. The jets of energy and particles that shoot out from the poles of some black holes can travel vast distances, compressing gas clouds and triggering the birth of new stars. These jets can even shape entire galaxies, carving out vast bubbles in the surrounding gas and dust. In this way, black holes act as cosmic sculptors, molding the structure of galaxies and influencing their evolution over billions of years. On an even larger scale, black holes might play a role in the universe's web-like structure. The cosmic web, a vast network of galaxies and dark matter, is thought to have formed from tiny fluctuations in the early universe. Black holes, with their immense gravitational influence, could have acted as anchors, pulling matter together and helping to form the dense nodes of this web. Without black holes, the universe might look very different, less structured, less organized, and perhaps less capable of supporting life. Interestingly, black holes also challenge our understanding of the universe's hidden patterns. Their event horizons, the points of no return, are places where the laws of physics as we know them break down. Studying black holes could reveal new insights into the fundamental nature of space, time, and gravity, potentially uncovering deeper patterns that govern the cosmos. For example, the recent detection of gravitational waves, ripples in space-time caused by colliding black holes, has opened up a new way to observe the universe, offering clues about its hidden structure. As we explore the role of black holes in cosmic order, we're reminded that even the most mysterious and seemingly destructive forces can have a profound impact on the universe's design. Whether they're regulating galaxies, shaping the cosmic web, or challenging our understanding of physics, black holes are key players in the story of the universe's hidden patterns. And with that, let's turn our attention to another elusive cosmic phenomenon, the mystery of neutrinos, and how these ghostly particles might hold the key to understanding the universe's earliest moments. Now, let's venture into the shadowy realm of neutrinos, particles so elusive they've earned the nickname ghosts of the universe. These tiny, nearly massless particles are everywhere. Trillions of them pass through your body every second, yet they interact so weakly with matter that detecting them is one of the greatest challenges in modern physics. But why should we care about these ghostly particles? Because neutrinos might hold the key to unlocking some of the universe's deepest secrets, from the fiery moments after the Big Bang to the intricate patterns that shape our cosmos today. Neutrinos are born in some of the most extreme environments in the universe: supernova, the cores of stars, and even the violent collisions of black holes. When a massive star explodes in a supernova, for example, it releases an enormous burst of neutrinos, carrying away most of the star's energy. These neutrinos travel at nearly the speed of light, unaffected by magnetic fields or even the pull of gravity, making them perfect messengers from the farthest reaches of space. By studying these particles, scientists can peer back in time to the universe's infancy, gaining insights into how the first stars and galaxies formed. But neutrinos aren't just relics of the past, they're also active players in the present. One of their most fascinating properties is their ability to change flavors as they travel. Neutrinos come in three types: electron, muon, and tau, and they can spontaneously switch from one type to another in a phenomenon known as neutrino oscillation. This bizarre behavior suggests that neutrinos have mass, albeit an incredibly small one, which challenges the standard model of particle physics. If neutrinos do have mass, they could be a piece of the puzzle in explaining dark matter, the mysterious substance that makes up most of the universe's mass but remains invisible to us. On a cosmic scale, neutrinos might also influence the universe's large-scale structure. In the early universe, neutrinos were so energetic that they moved freely, smoothing out fluctuations in the density of matter. As the universe expanded and cooled, neutrinos slowed down, allowing matter to clump together and form the galaxies and galaxy clusters we see today. This delicate dance between neutrinos and matter could have shaped the cosmic web, the vast network of galaxies and dark matter that defines the universe's structure. Detecting neutrinos is no small feat. Scientists use massive detectors buried deep underground or submerged in ice to shield them from other particles and radiation. One of the most famous neutrino observatories, the Ice Cube Neutrino Observatory in Antarctica, uses a cubic kilometer of ice to detect the faint flashes of light produced when a neutrino occasionally collides with an atom. These rare interactions provide a glimpse into the otherwise invisible world of neutrinos, offering clues about their origins and behavior. As we unravel the mystery of neutrinos, we're reminded that even the smallest particles can have a profound impact on the universe's grand design. From the explosive birth of stars to the subtle shaping of cosmic structures, neutrinos are silent witnesses to the universe's hidden patterns. And with that, let's turn our attention to another fundamental force that quietly shapes the cosmos: gravity, and its role in weaving the fabric of the universe. Now let's shift our gaze to a force so familiar yet so mysterious: gravity. Often thought of as the weakest of the fundamental forces, gravity is anything but insignificant when it comes to shaping the universe. From holding planets in orbit to sculpting the vast cosmic web, gravity is the silent architect behind the patterns and structures we see across the cosmos. But how does this seemingly simple force, which keeps our feet on the ground, also govern the grand design of the universe? At its core, gravity is the force of attraction between masses. It's what keeps Earth circling the Sun, the Moon orbiting Earth, and galaxies bound together in clusters. But gravity's influence extends far beyond these visible interactions. In the early universe, gravity played a crucial role in amplifying tiny fluctuations in the density of matter, setting the stage for the formation of galaxies, stars, and planets. Without gravity, the universe would be a featureless sea of particles, devoid of the intricate patterns we observe today. One of gravity's most profound effects is its ability to shape the cosmic web, the vast network of galaxies and dark matter that spans the universe. Imagine the universe as a canvas and gravity as the brush that paints the intricate filaments and voids of this cosmic masterpiece. As matter clumps together under gravity's pull, it forms dense regions where galaxies cluster, connected by thin threads of gas and dark matter. These threads, in turn, create the web-like structure that defines the universe's large-scale architecture. But gravity's role doesn't stop there. It also governs the behavior of black holes, some of the most extreme objects in the universe. Black holes, with their immense gravitational pull, can warp space-time itself, bending light and distorting the paths of nearby stars and galaxies. They act as cosmic engines, driving the evolution of galaxies by influencing the movement of gas and stars. In some cases, black holes even trigger the formation of new stars, creating a delicate balance between destruction and creation. Interestingly, gravity's weakness compared to other forces might be one of its greatest strengths. While the strong nuclear force binds atomic nuclei and electromagnetism governs chemical reactions, gravity's gentle pull operates over vast distances, allowing it to shape the universe on the largest scales. This unique characteristic makes gravity the key to understanding the universe's hidden patterns, from the distribution of galaxies to the expansion of space itself. Yet, gravity remains one of the most enigmatic forces in physics. While Einstein's theory of general relativity provides a robust framework for understanding gravity on cosmic scales, it breaks down at the quantum level where the other fundamental forces reign supreme. This disconnect has led scientists to search for a unified theory that can reconcile gravity with quantum mechanics, a quest that could reveal even deeper patterns woven into the fabric of reality. As we ponder gravity's role in the universe, we're reminded that even the simplest forces can have profound implications. From the tiniest particles to the largest structures, gravity quietly shapes the cosmos, leaving its mark on every corner of existence. And with that, let's turn our attention to another fascinating concept: how complex patterns emerge from simple rules, and whether this principle applies to the universe as a whole. Now, let's explore a fascinating idea that bridges simplicity and complexity: the concept of emergence. At its heart, emergence is the phenomenon where intricate patterns and structures arise from the interaction of simple, underlying rules. Think of it like this: a single ant following basic instincts might seem insignificant, but when thousands of ants work together, they create elaborate colonies, complete with tunnels, chambers, and even farms. This is emergence in action, simple behaviors giving rise to complex systems. In nature, emergence is everywhere. Consider a flock of birds. Each bird follows a few basic rules: stay close to your neighbors, avoid collisions, and match their speed. Yet, from these simple instructions, the flock moves as one, creating mesmerizing patterns in the sky. Similarly, snowflakes form from the simple interaction of water molecules, yet no two snowflakes are alike. These examples show how complexity can emerge from simplicity, often in ways that are unpredictable and beautiful. But does this principle apply to the universe as a whole? Many scientists believe it does. Take the formation of galaxies, for instance. The early universe was a nearly uniform soup of particles, governed by simple physical laws like gravity and thermodynamics. Over billions of years, these basic forces caused matter to clump together, forming stars, galaxies, and eventually the vast cosmic web we see today. What began as a simple set of rules led to the emergence of a universe filled with intricate structures and patterns. Emergence also plays a role in the behavior of complex systems, from weather patterns to the human brain. In weather, small changes in temperature or pressure can lead to dramatic outcomes like hurricanes or heat waves. In the brain, billions of neurons firing in simple patterns give rise to thoughts, emotions, and consciousness. These examples suggest that emergence isn't just a feature of the universe. It might be a fundamental principle that shapes reality itself. Yet, emergence raises profound questions. If complex patterns emerge from simple rules, does that mean the universe is inherently predictable? Or does the unpredictability of emergent systems hint at deeper, hidden layers of complexity? Some scientists argue that emergence points to a universe where order and chaos coexist, where simple beginnings can lead to infinite possibilities. As we reflect on the concept of emergence, we're reminded that the universe is a tapestry woven from countless threads, each following its own simple rules. Together, these threads create the rich, complex patterns we observe from the smallest snowflake to the largest galaxy. And with that, let's turn our attention to another intriguing idea: the role of information in the universe. and whether it might be the key to unlocking even deeper mysteries. Now, let's shift our focus to a theory that challenges the very fabric of reality, the idea that information might be the fundamental building block of the universe. Imagine for a moment that everything around us, stars, planets, even our own thoughts, could be reduced to bits of information. This isn't science fiction. It's a serious scientific proposition that has gained traction in recent years. At its core, this theory suggests that the universe isn't just made of matter and energy, but of information itself. Think of it like this: every particle, every force, every interaction could be seen as a piece of data in a cosmic code. Just as a computer processes information to create images, sounds, and actions, the universe might operate on a similar principle. The laws of physics, then, could be thought of as the algorithms that govern how this information is processed and transformed. This idea, known as the it-from-bit hypothesis, was first proposed by physicist John Archibald Wheeler, who suggested that every particle, every event ultimately arises from bits of information. But how does this connect to the hidden patterns we've been exploring? If information is fundamental, then the patterns we observe in the universe, from the spiral arms of galaxies to the intricate structure of DNA, might be the result of information being encoded and decoded in specific ways. For example, the way galaxies form and evolve could be seen as the universe processing information about gravity, dark matter, and other forces. Even the behavior of quantum particles, which can exist in multiple states at once, might be explained by the idea that they are, in essence, packets of information waiting to be read by an observer. This theory also opens up fascinating questions about the nature of reality itself. If information is the foundation of everything, does that mean the universe is, in some sense, a kind of computation? Could the patterns we see be the output of a cosmic program running on the hardware of space-time? Some scientists have even speculated that black holes might be the ultimate information processors, storing and transforming data in ways we're only beginning to understand. Yet, as intriguing as this idea is, it's not without its challenges. For one, what exactly is information in this context? Is it something physical, or is it more abstract? And if the universe is fundamentally informational, where does consciousness fit in? Are our minds, too, just complex arrangements of data? These questions push the boundaries of both science and philosophy, inviting us to rethink what we know about existence itself. As we ponder the role of information in the universe, we're reminded that the search for hidden patterns is as much about understanding the rules of reality as it is about uncovering the tools that shape it. And with that, let's turn to another captivating idea: the mystery of consciousness and its potential connection to the universe's hidden structures. Now, let's venture into one of the most profound and enigmatic questions of all: how does consciousness fit into the grand tapestry of the universe? This theory takes us beyond the physical and into the realm of the mind, exploring whether our awareness itself might be intricately connected to the hidden patterns that shape reality. Could it be that consciousness isn't just a byproduct of the universe, but a fundamental part of its design? Some scientists and philosophers propose that consciousness might play a role in shaping or even creating the patterns we observe. This idea, often referred to as the participatory universe theory, suggests that the act of observation itself could influence the way the universe unfolds. Think about quantum mechanics, where particles seem to exist in multiple states until they're observed. Could this mean that consciousness is somehow intertwined with the fabric of reality, acting as a kind of cosmic observer that brings order to chaos? Others take this idea even further, suggesting that the universe might be a kind of conscious entity itself. In this view, the patterns we see, from the symmetry of snowflakes to the vast cosmic web, are not just random occurrences, but expressions of a deeper, universal awareness. This doesn't mean the universe is thinking in the way we do. but rather that consciousness might be a fundamental property like space or time, woven into the very structure of existence. But what about our own minds? Are we, as conscious beings, uniquely tuned to perceive these hidden patterns? Some theories suggest that the human brain might be a kind of receiver for universal information, allowing us to decode the underlying order of the cosmos. This could explain why certain patterns, like the Fibonacci sequence or the golden ratio, feel so inherently beautiful or harmonious to us they might resonate with something deep within our own consciousness. Of course, these ideas raise as many questions as they answer. If consciousness is fundamental, how did it arise? Is it a product of complex systems like the human brain, or is it something more universal, existing even in the simplest forms of matter? And if our minds are tuned to perceive hidden patterns, what does that say about the nature of reality itself? Are we merely observers, or are we active participants in shaping the universe? As we explore these questions, we're reminded that the mystery of consciousness is not just a scientific puzzle, but a deeply personal one. It invites us to consider our place in the cosmos and the possibility that our awareness might be more than just a fleeting moment in the vast expanse of time. With that in mind, let's turn our attention to another fascinating piece of the cosmic puzzle, the role of quantum fluctuations in shaping the universe's hidden patterns. Now, let's shift our focus to the microscopic realm where the tiniest of events can have the most colossal consequences. Quantum fluctuations, those minuscule, unpredictable changes in energy at the smallest scales, might hold the key to understanding how the universe's grand structures came to be. Imagine the early universe as a bubbling, chaotic soup of energy and particles. In this primordial state, even the smallest fluctuations could ripple outward, setting the stage for everything we see today. These quantum fluctuations are thought to have acted like seeds, planting the first hints of structure in an otherwise uniform cosmos. As the universe expanded, these tiny variations grew, amplified by gravity over billions of years. What started as microscopic ripples eventually became the vast cosmic web of galaxies, galaxy clusters, and superclusters we observe today. It's a bit like blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots spread out, creating patterns that were once too small to see. But why do these fluctuations matter? Without them, the universe might have remained perfectly smooth, with no stars, no planets, and no us. It's these imperfections, these tiny deviations from uniformity, that allowed matter to clump together and form the building blocks of everything we know. Think of it as the universe's way of introducing a little chaos into the mix, ensuring that structure and complexity could emerge. Interestingly, these quantum fluctuations aren't just a relic of the past. They're still happening all around us, even in the vacuum of space. They remind us that the universe is never truly still, always buzzing with activity at the smallest scales. And while we can't see these fluctuations directly, their fingerprints are everywhere, from the distribution of galaxies to the faint whispers of the cosmic microwave background. So, what does this mean for the hidden patterns of the universe? It suggests that even the most random, unpredictable events can give rise to order on a grand scale. The universe, it seems, has a way of turning chaos into beauty, one quantum fluctuation at a time. With that in mind, let's move forward to explore another intriguing piece of the cosmic puzzle, the concept of eternal inflation and how it might explain the patterns we see across the cosmos. Now, let's take a step into the realm of the infinite, where the universe we know might just be one tiny bubble in an endless sea of possibilities. This brings us to the concept of eternal inflation, a theory that suggests our universe is not alone but part of a vast multiverse, constantly expanding and birthing new universes like bubbles in a cosmic foam. Imagine a pot of water boiling endlessly, with bubbles forming, growing, and popping. In this analogy, each bubble represents a universe complete with its own set of physical laws and constants. Our universe is just one of these bubbles floating in an ever-expanding ocean of space-time. But here's the fascinating part. Eternal inflation proposes that this process never stops. New bubbles, new universes are constantly being created, each with its own unique properties and patterns. So, how does this tie into the hidden patterns we observe in our universe? Well, if eternal inflation is true, the patterns we see, like the distribution of galaxies or the cosmic microwave background, might be the result of conditions set during the early moments of our bubble's formation. The quantum fluctuations we discussed earlier could have been amplified during this rapid expansion, creating the seeds for the structures we see today. But here's the kicker. In other bubbles, those patterns might look completely different, governed by entirely different rules. This theory also raises intriguing questions about the nature of reality. If there are countless universes out there, each with its own unique set of physical laws, what does that mean for the patterns we observe? Could our universe's patterns be just one possibility among an infinite array of outcomes? It's a mind-bending idea, but one that offers a potential explanation for why our universe seems so finely tuned for life. In a multiverse, it's possible that every conceivable combination of physical constants exists somewhere, and we just happen to live in the one where conditions are right for us to exist. Eternal inflation doesn't just challenge our understanding of the universe, it expands it quite literally. It suggests that the patterns we see might not be universal at all, but rather local to our cosmic neighborhood. And if that's the case, the search for hidden patterns becomes even more profound, as we're not just exploring one universe, but potentially an infinite number of them. With this cosmic perspective in mind, let's turn our attention to another force that shapes the universe's hidden patterns: magnetic fields, and their role in the evolution of galaxies, stars, and planets. Now, let's shift our focus to a force that's often overlooked but plays a crucial role in shaping the cosmos: magnetic fields. These invisible lines of force are not just confined to Earth or our solar system. They stretch across the vast expanse of the universe, influencing everything from the birth of stars to the structure of galaxies. But could they also hold the key to some of the universe's hidden patterns? Magnetic fields are everywhere in space, threading through galaxies, stars, and even the voids between them. They're generated by the movement of charged particles like electrons and protons, and can stretch across unimaginable distances. In galaxies, for example, magnetic fields help shape the spiral arms we see in images of galaxies like the Milky Way. They guide the flow of gas and dust, which in turn influences where stars form and how galaxies evolve over time. Without these magnetic fields, the universe as we know it might look very different. But magnetic fields don't just shape galaxies, they also play a vital role in the life cycles of stars. When a star is born, it forms from a collapsing cloud of gas and dust. Magnetic fields within that cloud can channel material into the star, helping it grow. Later, as the star ages and dies, magnetic fields can influence how it sheds its outer layers, creating stunning structures like planetary nebulae. Even the remnants of dead stars, like neutron stars, are home to some of the strongest magnetic fields in the universe, capable of bending space-time itself. And let's not forget planets. Earth's magnetic field, for instance, protects us from harmful solar radiation, making life possible. Other planets, like Jupiter, have magnetic fields so powerful they create auroras visible from space. These fields are not just byproducts of planetary formation, they're active participants in the cosmic dance, shaping the environments of planets and potentially influencing their ability to support life. So, do magnetic fields hold clues to the universe's hidden patterns? Some scientists think so. The way magnetic fields interact with matter and energy could be a key piece of the puzzle, helping us understand why the universe looks the way it does. For example, the large-scale structure of the cosmic web, the vast network of galaxies and dark matter, might be influenced by magnetic fields on a grand scale. These fields could guide the flow of gas and energy, shaping the distribution of galaxies and the patterns we observe in the cosmic microwave background. But here's the intriguing part: magnetic fields are not just passive players. They can amplify small fluctuations in the early universe, much like the quantum fluctuations we discussed earlier. This means they could have played a role in seeding the structures we see today, from the smallest stars to the largest galaxy clusters. If that's the case, then magnetic fields might be more than just a cosmic afterthought. They could be fundamental to the universe's hidden patterns. As we continue to explore the cosmos, magnetic fields remain a fascinating area of study. They remind us that even the most subtle forces can have a profound impact on the universe's evolution. And who knows, unlocking the secrets of magnetic fields might just bring us one step closer to understanding the grand design of the cosmos. With this in mind, let's turn our attention to another cosmic mystery: the unexplained acceleration of the Pioneer spacecraft, and whether it hints at hidden forces or patterns in the universe. Now, let's venture into a mystery that has puzzled scientists for decades: the strange case of the Pioneer spacecraft. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were designed to explore the outer reaches of our solar system. But as they journeyed farther from Earth, something unexpected happened. Both spacecraft began to experience a tiny but persistent acceleration that couldn't be explained by known physics. This phenomenon, now known as the Pioneer anomaly, has sparked countless debates and theories about what might be causing it. At first, scientists thought the anomaly might be due to something simple, like a fuel leak or thermal radiation from the spacecraft's power source. But after years of analysis, these explanations fell short. The acceleration was too consistent and too precise to be dismissed as a random error. This left researchers scratching their heads, wondering if they had stumbled upon a hidden force or pattern in the universe that we don't yet understand. One intriguing possibility is that the Pioneer anomaly could be evidence of new physics, something beyond our current understanding of gravity and motion. Some scientists have suggested that it might be linked to dark matter or dark energy, those mysterious components of the universe that make up most of its mass and energy but remain invisible to us. If dark matter or dark energy interacts with spacecraft in ways we don't yet comprehend, it could explain the anomaly. Alternatively, the anomaly might hint at modifications to Einstein's theory of general relativity, suggesting that gravity behaves differently on cosmic scales than we thought. Another fascinating angle is the idea that the Pioneer anomaly could be tied to the universe's hidden patterns. Just as magnetic fields and quantum fluctuations shape the cosmos, there might be subtle forces or structures at work that we're only beginning to detect. The anomaly could be a clue, pointing us toward a deeper understanding of how the universe operates on the grandest scales. It's a reminder that even in the vast emptiness of space, there are still mysteries waiting to be uncovered. Of course, not everyone agrees. Some researchers argue that the anomaly might have a more mundane explanation, like an unaccounted-for effect from the spacecraft's design or instrumentation. But even if that's the case, the Pioneer anomaly has already done something remarkable. It's challenged us to think differently about the universe and the forces that govern it. It's a testament to the power of curiosity and the importance of questioning what we think we know. As we continue to explore the cosmos, the Pioneer anomaly remains a tantalizing puzzle. Whether it's a sign of new physics, a hidden pattern, or something else entirely, it reminds us that the universe is full of surprises, and who knows? Solving this mystery might just lead us to discoveries that reshape our understanding of reality itself. With that in mind, let's turn our attention to another cosmic enigma: the theoretical concept of cosmic strings and how these one-dimensional defects in spacetime might influence the universe's structure. Now, let's unravel another fascinating thread in the cosmic tapestry: the concept of cosmic strings. Imagine the universe as a vast, intricate fabric woven together by the forces of nature. But what if this fabric had tiny, almost invisible flaws? These flaws, known as cosmic strings, are theoretical one-dimensional defects in spacetime, remnants of the universe's earliest moments. They're like cracks in the cosmic ice, formed when the universe underwent rapid changes in its structure during the Big Bang. Cosmic strings are thought to be incredibly thin but unimaginably dense, with a thickness smaller than an atom, but with the mass of an entire mountain packed into every inch. If they exist, they would stretch across the universe, forming a network of invisible threads that could influence the way galaxies and other large-scale structures form. Some scientists believe these strings might act as cosmic seeds, around which matter clumps together, shaping the universe's grand design. One of the most intriguing aspects of cosmic strings is their potential to create ripples in spacetime itself. As these strings move through the universe, they could generate gravitational waves, ripples in the fabric of reality that we've only recently begun to detect. These waves could carry information about the universe's earliest moments, offering us a glimpse into a time long before stars or galaxies existed. It's like finding a message in a bottle, written in the language of gravity from the dawn of creation. But cosmic strings aren't just relics of the past. They might also play a role in the universe's future. Some theories suggest that these strings could be responsible for creating cosmic voids, vast, empty regions of space where galaxies are few and far between. If true, this would mean that cosmic strings are not just passive remnants but active shapers of the universe's structure, influencing everything from the distribution of galaxies to the flow of dark matter. Of course, cosmic strings remain purely theoretical for now. No one has ever directly observed one, and their existence is still a matter of debate among scientists. But the search for these elusive threads continues, driven by the hope that they might hold the key to understanding some of the universe's deepest mysteries. Whether they're real or not, cosmic strings remind us that the universe is full of hidden patterns and structures waiting to be discovered. As we ponder the possibility of cosmic strings, let's shift our gaze to another cosmic oddity, the so-called axis of evil, a controversial alignment in the cosmic microwave background that has left scientists questioning whether the universe has a preferred direction. Now, let's turn our attention to a cosmic mystery that has left scientists both puzzled and intrigued, the so-called axis of evil. This peculiar feature in the cosmic microwave background, or CMB, has sparked intense debate and speculation. The CMB is the afterglow of the Big Bang, a faint echo of the universe's birth, and it holds a treasure trove of information about the cosmos. But within this ancient light, there's something unusual, a strange alignment that seems to defy our expectations. The axis of evil refers to an unexpected pattern in the CMB, where certain temperature fluctuations appear to align along a specific axis. This alignment suggests that the universe might have a preferred direction, a concept that challenges one of the most fundamental principles of cosmology, the idea that the universe is isotropic or the same in all directions. If true, this would mean that the universe isn't as uniform as we once thought, and that there's a hidden structure or bias influencing its large-scale behavior. Scientists first noticed this anomaly when analyzing data from the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite designed to map the CMB in unprecedented detail. The findings were so surprising that they were dubbed the axis of evil, a playful yet ominous name that reflects the discomfort this discovery has caused in the scientific community. Since then, other missions like the Planck satellite have also detected similar patterns, adding fuel to the debate. So, what could explain this mysterious alignment? One possibility is that it's a statistical fluke, a random quirk in the data that doesn't signify anything deeper. After all, the universe is vast, and sometimes patterns emerge purely by chance. But the odds of such a striking alignment occurring randomly are incredibly low, leading some researchers to consider more exotic explanations. Could it be evidence of a pre-Big Bang structure, a remnant of an earlier phase of the universe? Or perhaps it's a sign of something even more profound, like the influence of another universe beyond our own, as suggested by some multiverse theories. Another intriguing idea is that the axis of evil might be linked to dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy isn't evenly distributed, it could create subtle asymmetries in the CMB, leaving behind the patterns we observe. Alternatively, the alignment might be a clue about the universe's topology, its overall shape and structure. Could the universe be shaped like a torus or donut with hidden twists and turns that create this apparent directionality? Despite decades of research, the axis of evil remains one of the most baffling puzzles in modern cosmology. It challenges our understanding of the universe's origins and raises profound questions about the nature of reality itself. Is this alignment a cosmic coincidence, or does it point to a deeper, hidden order in the universe? For now, the mystery endures, reminding us that even in the vastness of space, there are still secrets waiting to be uncovered. As we grapple with the enigma of the axis of evil, let's shift our focus to the ultimate quest in physics, the search for a theory of everything, a framework that could unify all the forces of nature and reveal the universe's most fundamental patterns. Now, as we venture into the final frontier of our cosmic exploration, we arrive at the grandest quest of all, the search for a theory of everything. This ambitious endeavor seeks to unify all the fundamental forces of nature into a single, elegant framework, one that could explain everything from the tiniest particles to the vast expanse of the universe itself. It's a pursuit that has captivated the greatest minds in physics for over a century, and it holds the promise of revealing the ultimate hidden patterns woven into the fabric of reality. At the heart of this quest lies a fundamental question. Why does our universe operate under such a diverse set of rules? Gravity, electromagnetism, and the strong and weak nuclear forces each govern different aspects of the cosmos, yet they seem to operate independently of one another. For decades, scientists have dreamed of finding a way to bring these forces together under one umbrella, a unified theory that could explain how they all connect and interact. Such a theory wouldn't just solve long-standing puzzles in physics, it could also unveil the deepest symmetries and patterns that define the universe. One of the most promising candidates for a theory of everything is string theory. This groundbreaking idea proposes that the fundamental building blocks of the universe aren't particles as we once thought, but tiny, vibrating strings. These strings, existing in multiple dimensions, could give rise to all the particles and forces we observe, effectively tying together the laws of physics into a single, coherent framework. While string theory remains unproven, it offers a tantalizing glimpse into a universe where everything is interconnected, from the smallest quark to the largest galaxy. Another approach comes from quantum gravity, which seeks to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the force of gravity on cosmic scales. Yet, when these two theories are brought together, they clash, creating paradoxes that defy our understanding. A successful theory of everything would need to bridge this gap, revealing how gravity and quantum mechanics are two sides of the same cosmic coin. But why does this matter? Beyond the intellectual satisfaction of solving one of science's greatest mysteries, a theory of everything could unlock profound insights into the universe's hidden patterns. It might explain why the fundamental constants of nature, like the speed of light or the charge of an electron, have the precise values they do. It could shed light on the origins of the universe, the nature of time, and even the possibility of other dimensions or universes. In essence, it would provide a master key to understanding the cosmos in its entirety. Of course, the path to such a theory is fraught with challenges. The mathematics involved is extraordinarily complex, and experimental evidence remains elusive. Yet, the pursuit itself has already yielded remarkable discoveries, from new insights into black holes to the development of cutting-edge technologies. Even if a theory of everything remains out of reach for now, the journey toward it continues to push the boundaries of human knowledge, revealing new layers of the universe's intricate design. As we reflect on this monumental quest, one thing becomes clear. The search for a theory of everything isn't just about finding answers. It's about uncovering the profound beauty and order that underlies the cosmos. It's a reminder that, even in the face of the universe's vast complexity, there may yet be a unifying thread, a hidden pattern that ties it all together. And as we continue to explore, question, and dream, we move ever closer to glimpsing that ultimate truth. As we bring our journey through the cosmos to a close, let's take a moment to reflect on the incredible diversity of ideas we've explored. From the Fibonacci sequence weaving through nature to the holographic principle suggesting our universe might be a projection, each theory offers a unique lens through which to view the hidden patterns of existence. We've ventured into the mysteries of dark matter and dark energy, pondered the implications of quantum entanglement, and even questioned whether our reality could be a simulation. These theories, though varied, all point to one undeniable truth: the universe is far more intricate and interconnected than we often realize. What's remarkable is how these ideas, while distinct, often overlap and inform one another. The cosmic web of galaxies mirrors the fractal patterns found in nature, while the fine-tuning of the universe's constants hints at a deeper, perhaps intentional, design. Even the search for a theory of everything, as ambitious as it is, ties back to the notion that there's an underlying order waiting to be discovered. Each theory, whether grounded in mathematics, physics, or philosophy, contributes to a larger mosaic of understanding, one that's still very much a work in progress. But here's the thing: the quest to uncover these hidden patterns isn't just for scientists or philosophers. It's a journey that belongs to all of us. Every time we look up at the night sky, every time we marvel at the symmetry of a snowflake or the spiral of a galaxy, we're participating in this grand exploration. The universe invites us to ask questions, to wonder, and to dream. And while we may not have all the answers yet, the pursuit itself is what makes the journey so extraordinary. So, what do you think? Do these theories resonate with you? Do you see patterns in the world around you that hint at something deeper? Or perhaps you have your own ideas about the universe's hidden order? Whatever your thoughts, we'd love to hear them. Share your insights in the comments below, and let's keep the conversation going. And if you're as fascinated by these mysteries as we are, don't forget to hit that like button, subscribe, and ring the notification bell so you never miss an exploration into the wonders of the cosmos. Together, let's keep uncovering the secrets of the universe, one theory at a time.